So this is the last lecture of Chapter 4, Lecture 4, Part 5, solving trigonometric equations. So in as much as that we solve algebraic equations, we can solve trigonometric equations. So for example, suppose we want to find the values of x that satisfy 2 sine x minus 1 is equal to 0, and we want to solve it on an interval on the x-axis, that's equals. We want to solve it on the interval 0 to 2 pi. Okay, so we want to solve it here. And so, okay, so 2 sine x is equal to 1, and so sine x is equal to a half. So where does sine x equal to a half on the interval 0 to 2 pi? Okay, well, we should recognize the fact that on 0 to 2 pi, you can, if you don't have this memorized already, we know that x can equal to pi 6, or x can equal to 5 pi over 6. Okay, and if you need convincing, you can always look at the graph. Okay, all right, now, so that's the solution on 0 to 2 pi. So what about the solution on the entire x-axis? Now, we know that the sine function exists everywhere on the x-axis. Right? And we also know the following. We also know that the sine function is periodic with period 2 pi. So we know this to be the case, where n is an integer. Okay? So we can take the solution on 0 to 2 pi right here, and we can add integral multiples of 2 in pi, or 2 pi, integral multiples of pi, 2 pi that is. So on the entire x-axis, n is an integer, these would be solutions. Okay, we could have pi 6 plus 2 in pi, or 5 pi 6 plus 2 in pi. And you can plug in any integer you want for n, say like -4. So if you add -8 pi to 5 pi over 6, well, that would be a solution to this equation as well, okay, because of periodicity. All right, now, okay, so let's do some more examples. How about we want the tangent squared of x minus 3 is equal to 0. Okay, so we can solve this on, we can find a solution on, say, the open interval -pi12 to pi halves. Okay, because that's essentially where one period of the tangent function is. Okay, so let's say tangent squared x is equal to 3, and then the tan x is equal to plus or minus the square root of 3. Okay. All right. Now, so the tangent of what is equal to the square root of 3, or minus the square root of 3? We know that on -pi12 to pi halves, the tangent of pi thirds, is equal to the sine of pi thirds divided by the cosine of pi thirds. Okay, and hopefully you have it memorized by now. That's equal to the square root of 3 over 2 divided by 1/2, which is equal to the square root of 3. So the tangent of pi thirds is equal to the square root of 3. And we also know that the tangent function is an odd function. So, well, before I proceed with that, bear in mind that pi thirds is in the interval from -pi12 to pi halves. Okay, so now, moving on, the tangent is also an odd function. So we know that the tan of -pi thirds is equal to the negative of the square root of 3. And negative pi thirds, of course, is on this interval as well. So on this interval, on the interval negative pi halves to pi halves, if x is in this interval, okay, the solution would be x is equal to pi thirds, or x is equal to negative pi thirds, right? And now, okay, so now what if we want the solution to the original equation on the entire x-axis? Well, we know that the tangent function is periodic with respect to integral multiples of pi. So we know this. The tangent of x plus n pi is simply equal to the tangent of x. Okay? And so since x is pi thirds, we can add integral multiples of n pi to pi thirds or to negative pi thirds. So the solution to this equation on the entire x-axis is x is equal to pi thirds plus integral multiples of pi, or x is equal to negative pi thirds plus integral multiples of n pi. So these would be the set of values of x. So there are an infinite number of values of x that satisfy this equation. And this is how you would specify it. Put an or statement there. Okay. All right. So how about this? We find a solution to sine x minus cosine x is equal to 0. Okay. So in this case, of course, we want to know where sine x is equal to cosine x. All right, so where does that happen? Well, if we divide both sides of the equation by cosine x, we're left with the tangent of x is equal to 1. And so solutions to this would be x equals pi fourths, and then because of the periodicity of the tan function, we can add integral multiples of pi, okay? And you might want to say that n is an integer. N is the element of the set of integers. Uppercase J is the set of integers. All right. Okay. All right, so let's solve, say, 2 cosine squared x minus 7 cosine x plus 3 is equal to 0. Okay, so it's a quadratic in the cosine function, right? So perhaps we can factor it. So let's explore being able to factor that using, the techniques from algebra. So we could go 2 cosine x minus 1 times cosine x minus 3 is equal to 0. Okay. All right. So yeah, so that would be the factorization. So we said each of the factors equal to 0. Well, in this case, for this factor, we would require that cosine x is equal to 3. And obviously that can't happen because cosine x can never be greater than 1. So no solution for this factor, right? No need to process that. But this factor does have a solution. So we can set 2 cosine x minus 1 equal to 0. So cosine x is equal to 1/2. So where does cosine x equal to 1/2? Well, that would happen at wherever cosine x is positive, so that would be in quadrants 1 and 4. And so we know x could equal to pi thirds. That would be its quadrant 1 value. Or x could equal to, say, 5 pi over 3. That would be its quadrant 4 value. And then since we want the solution on the entire x-axis, the complete solution would be the periodic extension of pi thirds for cosine. So that would be 2/3 pi thirds plus 2n pi, or 5 pi over 3 plus 2n pi. All right, see how that works? Okay. All right, next question. So how about we solve 1 plus sine x is equal to, say, 2 cosine squared x. Okay, so we can replace cosine squared x with its Pythagorean identity. So that would be 1 minus sine squared x. All right, so now we have we can formulate a quadratic expression in sine. So we have 2 sine squared x plus sine x, and then subtract 2 from both sides, minus 1 is equal to 0. So it's quadratic in sine, so now we can factor it, probably. So we have 2 sine x sine x, okay, plus 1 minus 1. Okay, and so now each factor has a solution. So try the first factor, so we need to solve 2 sine x minus 1 is equal to 0. So sine x is equal to a half. And where does that happen? That would happen at pi 6, right? Pi 6 or at 5 pi over 6. So these would be the two values of x that would solve that. And then we need to solve sine x is equal to negative 1. And so where does that happen? That happens at x equals to 3 pi over 2. Okay, and then all we need to do then is do the periodic extensions. So the solutions would be pi 6 plus 2 in pi. Okay, 5 pi over 6 plus 2 in pi. And then, of course, 3 pi halves plus 2 in pi. All right, so they're the solutions. All right, okay, simple enough. Next problem. So how about we solve this equation? Sine 2x minus cosine x is equal to 0. Okay, so we can do the expansion of sine 2x. Sine 2x is 2 sine x cosine x minus cosine x is equal to 0. Then we can factor out the cosine x. Okay, and then we set each factor equal to 0, so where does cosine x equal to 0? Okay, so that would happen at x equals to pi halves, or at x equals to 3 pi over 2. Okay, and then we solve where 2 sine x minus 1 is equal to 0, and that would happen where sine x is equal to a half. And again, that's pi 6 or 5 pi over 6. Okay, maybe there's too much emphasis on that one. Okay, so then we can consolidate our answers and do the periodic extension. So x is equal to pi halves plus 2 in pi, 3 pi over 2 plus 2 in pi, pi 6 plus 2 in pi, and then 5 pi over 6 plus 2 in pi. Okay, so that would constitute your answers. Okay, so one more. Let's do another one. How about we solve this equation? Say cosine x plus 1 is equal to sine x. And we want to solve it on the interval 0 to 2 pi, so we don't care about periodic extensions. All right, so we can square both sides. So cosine squared x plus 2 cosine x plus 1. And the reason why we want to square both sides is so that we can get rid of the sine term. We can express the sine in terms of cosine. So all we have is an equation in terms of cosine. Okay, so by the Pythagorean identity, sine squared x is 1 minus cosine squared x. Now be careful, you may have the possibility of extraneous solution. So setting up the quadratic equation in cosine x, we have 2 cosine squared x plus 2 cosine x is equal to 0. Okay, and so now we can factor out a cosine x, probably divide the equation by 2 as well. So cosine x times cosine x plus 1 is equal to 0. Okay, and so cosine x is equal to 0. The one solution, so that means x would equal to pi halves or 3 pi over 2. And then we have the other factor, cosine x is equal to what? Minus 1. And so the only place where cosine x equals to minus 1 on the interval would be x equals to pi. So those are your solutions, 3 solutions there. Okay. All right, here's an interesting one. So let's solve 2 times the sine of 3x minus 1 is equal to 0. All right, so in this case, we'll have sine 3x is equal to a half. So we require then that 3x equal to pi 6 or 3x equal to 5 pi over 6. Okay, and so for periodicity, okay, so the complete solution on the entire x-axis, 3x is equal to pi 6 plus 2m pi, or 3x is equal to 5 pi over 6 plus 2m pi. Okay. Okay, so now solving, dividing both sides by 3, of course, we'll have x is equal to pi 18th plus 2/3 in pi. And or x, not or, yeah, or x is equal to 5 pi over 18 plus 2/3 in pi. Okay, now suppose we want the solution to this equation only on the interval 0 to 2 pi. Okay, so if we were to do that, then we would only need positive values for n, and so we can start off with saying n is equal to 0. So if n is equal to 0, we would have pi 18ths and plug in n equals 0 here, 5 pi over 18. So those two numbers are in the interval. As long as it's less than 36 pi over 18, we're good, right? And greater than 0. Okay, so if n is equal to 1, that would be 13 pi over 18 for that one. And if n equals to 1 here, that would be what? 17 pi over 18. If n were equal to 2, that would be 25 pi over 18, right? And let's see, 10. N were equal to 2, it would be 4, 6, yeah, 25 pi over 18. And if n were equal to 2 here, that would be 29 pi over 18. And so I think that's as far as we can go with n. If n were larger, it would be outside the interval. So this would be the solution on the interval 0 to 2 pi. All right, so let's work another one. How about the square root of 3 times the tangent of x over 2 minus 1 is equal to 0. So in this case, we want to solve for x. So the tangent of x over 2 would equal to 1 over the square root of 3. Okay, and so this would imply that x over 2, so if you've got your table memorized from, say, chapter 2, this would imply x over 2 is equal to pi thirds. And if you need convincing, just take sine of pi thirds over cosine of pi thirds, and you should get 1 over the square root of 3. So, based on the periodic extension, we require that x over 2 is equal to pi thirds plus 2n, not 2n, n pi, excuse me, because the period of the tangent function is pi. Okay, so that would be pi thirds plus n pi. And so x is equal to 2 pi over 3 plus 2n pi. Okay. All right. And so what are the solutions on the interval 0 to 4 pi? Okay, well, again, we're only interested in positive numbers, right? Okay, so we can start off by plugging in n equals 0. So if n equals 0, we'll have 2 pi over 3. Video, what are you doing to me? So if n is equal to 0, we have 2 pi over 3. If n equals to 1, we'll have, what, 8 pi over 3? All right, 2 pi, 6, yeah, 8 pi over 3. So as long as we're less than 12 pi over 3, we're good. If n equals to 3, we'll have 6. Yeah, so that's as far as we can go. Okay. All right. Last problem of the section. Well, no, we still have a couple more to do. Okay, so let's solve for x in this expression. Tangent squared x minus tangent x minus 2 is equal to 0. Okay, so this is quadratic in the tangent function, so we can factor it. So this would be tan x minus 2 times the tangent x plus 1. Tangent x plus 1 is equal to 0. Okay, so we require that tan x equals to 2, which you can, or tan x equals to negative 1. So we know, in this case, x is equal to minus pi fourths. Okay, or 7 pi over 4. Okay, so if we were just to solve it on, just to solve this equation on negative pi halves to pi halves. Okay, we'll just solve it on this domain, and then x equals to negative pi fourths. Okay, because this will be the domain of the principal tangent function. All right, and so, the solution to this one, of course, would be x is equal to, well, we don't know precisely what that would be, so we can just write tan inverse of 2. All right, so now, by periodic extensions, then, the solutions would be tan inverse of 2 plus n pi, and then negative pi fourths plus n pi. And so your 7 pi over 4 would fall in here. Okay. let's see. Let's see. Yeah, for n were say 2. If n were 2, then 2 pi plus minus pi fourths would be 7 pi over 4. Okay, so one more problem. This one will require the use of an illustration. So how about we solve this? 3 sine x minus 2 is equal to 0. Okay, so this will require that sine x is equal to 2/3. Okay, so now let me draw a picture. Bear with me while I pull up an illustration that's relevant to the solution of this problem. I thought it was there. I guess it's not there. Ah, okay. Well, it's not there then. It didn't get, okay, so this didn't get included in the lecture notes. All right, so I'll go ahead and draw the picture then. All right, so let's draw the picture of the unit circle. Well, actually, I don't have to draw it. I think we've got one, right? We have a tool. So I don't have to be so sloppy about it. So here are our coordinate axes. And let's see, we put, okay, so suppose this is our unit circle. All right, so now the sine of theta is 2/3. So that means that, where is 2/3? The sine of theta, okay, so we know that such an angle would probably be less than pi halves, right? So 2/3 essentially is, 2/3 is essentially where? Right about the sine of theta is 2/3, so perhaps 2/3 could be here. So here's theta. Okay? And then we know that, okay, we'll have two solutions, right? Because this is, the reference angle theta is here as well. And so, oops, let me draw that a little bit better. So we know by reflection about the y-axis, the sine will take on duplicate values, okay? That is, okay, whatever the sine of 2/3 is, the sine of this angle will be 2/3 as well, okay? Because this angle is theta. So the question is, okay, so in quadrant 1, okay, x is equal to the inverse sine of 2/3, and we can get away with that. Okay, so in quadrant 1. Now in quadrant 2, okay, we have theta, or x in this case. X must equal to, I'm sorry, that should be in terms of x. Sorry, I switched variables on you. Sorry about switching variables. It should be in terms of x. Okay, so here's x. The sine of x is 2/3. So that means the ordinate of this point is 2/3, okay? And then by reflection, or symmetry, so is the ordinate of this point. Okay, and so this angle is x as well. So we know that x must equal to pi. Now this x is not the x on the x-axis. This is just the input, okay? So x must equal to x minus the sine of inverse of 2/3. Okay, so this problem has two solutions on the unit circle. Okay, so now by periodicity, all right, so by periodicity, x must equal to sine inverse 2/3 plus 2 in pi, or x must equal to pi minus sine inverse of 2/3 plus 2n pi. Okay, so those are the solutions, infinite solutions. Okay, so that concludes Chapter 4 lecture notes. So what does that mean? That means you have to have your web assignment for Chapter 4 completed, and we have our Chapter 4 test. Okay, and so please prepare for your test. As usual, if you have any questions, see me during my office hour, or email me. Again, don't spend too much time fretting over solutions to your WebAssign homework problems. If it takes you longer than 10 minutes to work a WebAssign question, send me an email requesting assistance, and I'll post a hint on the class website. All right, so next chapter will be Chapter 5. So that's it for 4.